Okay, so what we're going to do then is let's go through and substitute what we've got into our integral form to see how that plays out. So seeing how we get that q dot, let's first write out what we would get for q dot. So Fourier's law, again, says q dot double prime at the surface is going to be minus k partial t with respect to y, evaluated at y equals 0. So that would be minus k partial with respect to y of my temperature. My temperature is that thing up there. But I have to solve that for t, just to be on the left-hand side. So that's t infinity minus ts times 2y over delta t. Minus y over delta t squared, evaluated at y equals 0. And then that has to equal, that simplifies down to, k times ts minus t infinity times 2 over delta t, right? Because t infinity minus ts is constant. You take the derivative of this stuff, and then you end up with what's over here. Right? So that's just Fourier's law. So okay, we have that. Now let's substitute everything together into the integral form. So the integral form for us was d dx of the integral from 0 to delta t of u times t minus t infinity dy is equal to q dot double prime s over rho c. So let's see, we have this thing over here, the thing we just solved for. That's q dot double prime s. Our temperature solution up here, so this gives us our temperature. Or we can solve for temperature there. So then we just substitute all that stuff in. The one thing that's maybe a little bit unclear is I have u here. So what do I have to somehow have a velocity profile that goes with this. What you can do is you can just take, if you've already done the momentum part of it, you can just take the u that you've already got and then substitute that in. But it doesn't have to be the same u, right? It makes it easier. You've already done the work. But let's take a velocity profile and substitute that in. Let me just rewrite that. That was u over u infinity is equal to 2y over delta m minus y over delta m squared. So if we substitute all that in to the integral form, we get d dx of the integral from 0 to delta t of u, so u infinity times 2y over delta m minus y over delta m squared times temperature. So temperature is Ts plus 2y over delta t minus y over delta t squared times t infinity minus ts. Minus then t infinity. Okay, all of that then dy. Then let's see. That was the end of the integral, and then that has to equal on the right-hand side. Let's see. Let me just bring it down here. So that equals 1 over rho c times conductivity k ts minus t infinity times 2 over delta t. Okay. What do we have again? So we have u, right? U is this stuff here. We have t, so t is this term here, minus t infinity, and then all that's in the integral. And then on the right-hand side, we have 1 over rho c times q dot s, which is this thing here.
I found this on the web.
All right. Maybe I do need help. So yeah, so we have all this. This is our integral form. Now we need to evaluate this for the integrals. One maybe issue here, right? We have in this delta m here, and we have delta t. So it's kind of a problem, I guess. We're trying to get an ODE in terms of delta t alone. One way to deal with this, it's an approximation, is to say that I know the relationship, generally speaking, between delta m and delta t. Okay. Now, just stepping back for a second, we're solving for delta t here. We've already solved for delta m in some other way. But we have an analytical expression. It'd be hard to substitute that in here maybe and solve it explicitly. I can say approximately, I know the relationship between delta t and delta m is the square root of the Prandtl number. Right? Now that's not exactly right because we're solving for the delta t's here, or the deltas here, but approximately it's right. So wherever you see this delta m, for purposes of this equation, we can substitute in, say, square root of Prandtl times delta t as my delta m, and then I have an expression that's just in terms of delta t. Okay. And why is that okay? I guess mathematically it's probably like a little bit, you're not quite doing the right thing, but this whole thing is already an approximation, right? The integral technique is already an approximation. We're already saying we're assuming a profile, let's just go with it. So like, what's the harm in being a little bit more approximate, right? I guess that's the takeaway. So we would say, I know my Prandtl number to the 1/2 power is equal to, say, delta. So let me make sure that gets this substitution right. So I would say delta m over delta t, right? You could also say it's those squared. So I'm going to make the substitution based on that and then move forward with my ODE. Okay. So let's look at how this plays out. So I have all this stuff written out. One other thing before we actually go through and solve it. Let's look at the equation up here on the top. This should be what we just wrote. So I have my u, my t, my q dot. What happens if my temperature profile is, say, going outside of the range of the valid model of u? So what happens if my Prandtl number is less than 1? If it's less than 1, then once I get my temperature profile outside of the valid region for u, then this profile stops being correct, right? The velocity profile is no longer correct if your temperature is outside of that velocity profile. Think about what I'm saying there. So this model is only right from 0 to delta t. Beyond that, it sort of loops back on itself and it's wrong, right? It's the wrong solution. So what you need to do is we have to put conditions on this. This equation is only okay, as it's written, if Prandtl number is greater than 1. Right? If it turns out that the velocity boundary layer is thicker than the the thermal boundary layer. If that's true, then you're always safe inside the U region and you're good. So what do you do if that's not the case? Like there's plenty of fluids where Prandtl is not greater than 1, like air, right? So what do? Well, I have to break it up. So we would say, I'm going to break this up into two integrals. The first integral would be, I'm just going to integrate from 0 to delta m. So note up here, this is 0 to delta t. So I'm breaking it up and say 0 to delta m. I'm going to do my conventional solution in terms of the velocity profile. Then once I hit that boundary, then I integrate just from the edge of the momentum to the edge of the thermal boundary layer, where u now just becomes u infinity, because now we're outside of the boundary layer. So u infinity times the temperature, and then the right-hand side stays the same. So now you have basically two integrals to do, but it's not. This is certainly going to be easier, right? Because you have just a constant times the temperature profile. All right, so that's fine if it turns out, in some case, that the Prandtl number is much, much less than 1, meaning your temperature boundary layer would be much, much bigger than your velocity boundary layer. then you can make the approximation to say, approximately, my velocity is u infinity everywhere. And then you just stop worrying about the u altogether, and you just have that constant, and it's a pretty good way of modeling it. Okay, so you have these different conditions that you have to follow through. Okay. Questions on that part of it? So then let's go through the final steps here to get the actual ODE. So we have our integral form of our equation up on the top. What we're going to do is make that Prandtl substitution. So let's see. Yeah, let me just figure this out. Okay, so let's rewrite this a little bit. So we have the integrals in terms of just the constant stuff on the outside. So rewriting this a little, just d dx times u infinity ts minus t infinity, just pulling out some constants. Now from 0 to delta t of the velocity profile, which is y over delta m minus y squared over delta m squared, squared times 1 minus 2y over delta t plus y squared over delta t squared dy is equal to k over rho c times t s minus t infinity delta, or sorry, 2 over delta t. Okay, so just rewriting it that way. So then we make this substitution, which is, let's see, we're going to say delta m over delta t. Anytime we see that, we're going to call that equal to Prandtl to the 1/2. Evaluating out the integrals, I'll just kind of skip to the result here. We would get the following equation. So we would get delta t squared over 6 delta m minus delta t squared over 30 delta m squared equals delta t times 1 over 6 square root of Prandtl minus 1 over 30 Prandtl. So to be clear, the steps here do involve making an assumption about the relationship based on the Prandtl number. It's an approximation. When you make that assumption, then you can substitute in and rewrite this stuff. So this is just our integral. Now we substitute in for Prandtl, and we have an ODE that is in terms of delta t only. I guess the delta m is implied here, but we assume Prandtl's a constant. Okay? Okay. Okay, so then what does our ODE become? So we substitute this back into the differential equation, and we get this. We get d dx of u infinity ts minus t infinity of that thing we just, the integral we just evaluated, which was, by the way, it was just this integral right here. This integral right here. That integral gives us this result. So putting that back in, we get delta t then times 1 over 6 Prandtl to the 1/2 minus 1 over 30 times Prandtl. And then that's equal to k over rho c times ts minus t infinity times 2 over delta t. Okay, so we can solve this in terms of this ODE in terms of delta t. So you have this constant stuff. This can come out. This whole term here is also a constant. Prandtl we're assuming is a constant. So the only thing that's left is a bunch of constant stuff times d delta t dx. And then on the right-hand side, you have k over rho c. This is all constant, delta t. Right, so you can solve this ODE. It's separable. We can get a result here.